Over 1 million robots are at work in factories all over the planet. And every year, 100,000 new industrial robots and more are purchased, with numbers led by factories in Japan, China, the United States, Korea, and Germany. These robots help us manufacture cars, electronics, medical devices, medicines, pharmaceuticals, food and beverages, metals, chemicals, plastic, and rubber. Lots of stuff. One of the largest producers of the industrial robots is the German company KUKA, which has been building robots since 1973. And robots even help us manufacture other robots, something the Japanese company Fanuc pioneered back in 1985. There are even robots to maintain other robots. Virtually all of these robots are not humanoids. They're specialized robotic manipulators, and their workplace is the highly structured, highly predictable world of the industrial factory. The tasks of robotic manipulators involve repetitive, quick, and highly accurate movements to grasp, move, manipulate, assemble, and tool. With tools in hand, these robots can file and paint and assemble, cut, polish, flame, weld, bond, glue, and seal, inspect, and sort. Industrial robots all began as variations on a theme, a robotic arm. The link is a rigid body that maintains the distance between joints and often contains the motors that power the movement of neighboring joints. The joint of a robotic manipulator is usually of one or two types: revolute or prismatic. Revolute joints rotate or revolve, and prismatic joints slide. We humans have mostly revolute joints, and many of these joints revolve around a hinge, so-called hinge joints. Now, a classic hinge joint is our elbow, and I've got an upper arm and two lower arm bones of a human skeleton here. So an elbow rotates through a single kinematic degree of freedom. Kinematics is the study of motion without considering the forces that generate those motions. If you include forces in your study of motion, it's called dynamics. So kinematics and dynamics are hugely important in factory robots because we want a machine whose motions can be controlled precisely, and you have to control those motions by understanding forces as well. Now, when a joint has a single degree of freedom, in kinematic terms we say its position can be described with a single mathematical variable, which we typically measure, in a revolute joint anyway, as an angle. So your elbow has a single degree of freedom that can rotate through an angle of about 150 degrees or so. Now, anatomy is at once an inspiration and a challenge for roboticists. Let me take you through a wonderful joint that we all possess, the shoulder joint. Technically, it's known as the glenohumeral joint. The glenohumeral joint is sometimes called a ball and socket joint because the head of the humerus is hemispherical, half a ball, and fits into a socket. This depression in the scapula, the shoulder blade, is called the glenoid fossa. I have here, this is the forelimb of a pig, to show you the head of that humerus bone right here. Here's the scapula or shoulder blade, and they come together in that ball and socket joint. So the head of the humerus can rotate in 3 rotational axes, each with their own range of motion. I actually can't do it on this skeleton because it's linked together in order to keep it in one place. Now, let me do it with my arm instead. If you think about my arm here as an aerial vehicle, we talk about 3 axes of rotation. So there's pitch, which is up and down, yaw, this way, and roll, this way. Now, in anatomy, we talk about abduction, which is going this way, so that upper arm moving away from the body. Adduction is the opposite for pitch. For flexion and extension, we have this going this way, up and down, and medial rotation is this rolling motion I was doing. Medial rotation and lateral rotation. So how is all this motion controlled? Well, depending on how you partition and name your muscles, one shoulder joint has motion controlled by at least 10 different muscles. Now, let me show you something amazing that our shoulders can do. I'm going to close my eyes and, you ready? Clap my hands. I know it doesn't seem amazing, but As we get older, we're very happy to be able to do simple things like that. But really, what's amazing is that I not only controlled 10 muscles in both of my shoulders on both sides, but I also controlled the rest of my muscles in my arms and my wrists. Blind, I was able to take all of these motors and degrees of freedom, plan and then enact a collision between my end effectors, my hands. Now, what makes this possible for all of us is that we have what is called proprioception, a bunch of sensors that notice the position of our joints and the effort of our muscles. These sensors are stretch receptors embedded in our ligaments and tendons. I can clap my hands with my eyes shut or open because this is all about sensor-guided movement. Even though this is easy for us, for a roboticist, coordinating even just 10 different motors though, a single arm is a nightmare. So many motors make predictable, accurate control of motion extremely difficult, even when you have sensors to monitor every position of every joint. So what's a roboticist to do? Designing robotic manipulators always involves trade-offs. And those trade-offs come between the range of motion and the control of that motion. So one common engineering trick is to constrain every joint to be a single degree of freedom. This allows you to simplify the motion and its control. Then you can add degrees of freedom back in with you can add those degrees of freedom back in with more single degree of freedom joints. You can also make more complex joints like the ball and socket, but you just won't find these on most robotic manipulators, and that's because the fundamental function of a robotic manipulator is simple pick and place. Pick and place. Picking something up and placing it somewhere else. Humans have been doing this for as long as we've been on 2 feet, picking fruit, wielding tools, right? The first record we have, on the other hand, of a programmable pick and place robot is actually quite recent, from 1938. Griffith P. Taylor published an article called An Automatic Block Setting Crane, Mechano Model Controlled by a Robotic Unit, and he published this in Mechano magazine. Now, at first glance, his model looks like a fancy toy. But if you read the article, you can see this system is programmable, and that's really fantastic. What the machine does is to pick up a series of bricks and create a circular stack automatically in about 50 minutes. If we look at the degrees of freedom in joints in Taylor's robot, we see that it has one rotational degree of freedom that allows the arm to swing around. It has another rotational degree of freedom that allows the grip out at the end of the dangling cable to swivel. And then the gripper itself has jaws that rotate to hold the bricks. These joints are all revolute. In addition, Taylor's robot has 2 translational degrees of freedom with prismatic joints. Let's look at these joints carefully. This is the equivalent of being able to change the length of the sections or linkages on your arm. First, the rigging that's hanging down can move in and out along the main truss that creates the horizontal part of the arm. Translational degree of freedom number 1. Second, the cables themselves, arranged in block and tackle scheme, can change their length, raising or lowering the grippers. That's translational degree of freedom number 2. In total, Taylor's robot has 5 degrees of freedom to allow it to pick and place bricks. It is automatically controlled and reprogrammable by the tape that Taylor mentions in his article. Taylor's pick and place robot from 1938 fits the international definition, by the way, for industrial robots, which was created by the International Organization for Standardization, and it's listed as ISO number 8373. Quote, automatically controlled, reprogrammable, multi-purpose manipulator, programmable in 3 or more axes, which may be either fixed in place or mobile for use in industrial automation applications. End quote. Very cool. So you can see why some people consider Taylor's invention to be the very first robotic manipulator ever. Now, as so often happens, it takes years for an idea for a robot to be translated into commercial applications. The first U.S. patent for a commercially successful industrial robot was actually granted in 1961 to George Duval. The patent was called Programmed Article Transfer. Not particularly exciting title, I know, but what it did was really important. Article transfer is a fancy name for pick and place. What you see when you look at the figures from this patent are tracks along which the transfer apparatus moves. Parallel to those tracks runs a conveyor belt. The arm of the transfer apparatus reaches across the conveyor belt, grabs cartons from the pallets, and then transfers those cartons back to the conveyor belt. A far-sighted feature of Duvall's patent was a feedback loop between the sensors detecting the position and the program controller. So Duvall's patent envisioned the robot knowing that its arm or gripper has gotten into the right position because a sensor detects that motion. So think about all the sensors that are in our arms or in the arms of Baxter. So just like as we've been talking about, when it works, this is proprioception, though reliable sensor-based movement turned out to be an ongoing challenge for robotics. Now, by the time that Duvall received his patent in 1961, he'd already formed a company back in 1956 when he had first applied for the patent. The company, formed with serial entrepreneur Joseph Engelberger, was called Unimation, which was short for Universal Automation. Unimation became the first company to build robots that went to work for industry, and those robots were called Unimates. The first Unimate robot was installed in 1962 in a General Motors factory, the Inland Fisher Guide plant in Turnstead, New Jersey. GM used the Unimate to lift hot pieces of metal from a die casting machine and stack them. In this classic film, taken in the 1970s, you can see a Unimate in action. The worker is first adjusting the gripping system for the task at hand. You're actually going to see several different Unimates here. The first is showing off in the showroom, swinging around, raising and lowering its arm. Then it rotates its gripper, extends its arm, and picks up an object. I count 5 degrees of freedom there. Then, precision placement of objects into a hole is what we see next, where a Unimate is on an assembly line, picking up hot die cast metal, cooling it off in a water bath, and then placing the piece on a conveyor belt. Accurate, repeatable control of robotic manipulators was critical for their development, and 2 different ways of thinking about movements developed: forward and inverse kinematics. In both approaches, we are interested in the position and orientation of that end effector, the hand, just like when we grab something. In forward kinematics, we can compute the end effector position by measuring the joint angles and knowing the lengths of the links. Trigonometry will do the trick mathematically, and it allows us to transform what we call the joint space of angles into the Cartesian space of the XYZ coordinates of the effector. Now, with forward kinematics, it's easy to move the robot and then calculate its position. In inverse kinematics, we pose the problem the other way around. This may be much harder to do. First, we have to identify the position that we want the end effector to occupy, and perhaps some constraints about the path to take, and then calculate the movements of the arm that will do the job. We can think of that inverse kinematics problem this way. If we want the end effector to be at position XYZ, then calculate all possible combinations of joint settings that would make that possible. Now, we've already talked about the trade-off between the range of motion and the control of motion, and inverse kinematics is the formal way to wrap our heads around that problem. Let's start with a simple example of design, an arm with a single degree of freedom. Like here, actually, in Clawbot, where we have just a single degree of freedom in that joint. So we have a revolute joint with a base and then a linkage here. If you know the length, or the radius in this case, of the linkage, then the angle of 45 degrees, right, tells you exactly where the arm and the end effector is in the plane of rotation. So you can see right away that the problem with a single degree of freedom is that the tip of your robotic arm, where you are likely to have a gripper or something that's holding on and doing some work, you can't be in very many places, right? It can only be along that circumference. That end effector is constrained to that circumference. So how do you set it free? Well, you add a second hinge joint. So now your arm has 2 degrees of freedom. To describe the position of the tip of the arm, you need the angle that describes the position of the 2 linkages of the arm. In the case that I've got, the position of the arm is described by just 2 numbers then, 45 degrees and, let's say, negative 30 degrees. So now we can think of how a controller might control the motion and position of the arm. Let's call our original joint, joint A. The second joint we added, joint B. The plan that the controller is putting into motion is to tell the actuators, which are the motors that control the position of each joint, to move joint A to 45 degrees and joint B to negative 30 degrees. Now, given this trade-off, one of the most important things to consider when building or buying an industrial robot is the minimum number of degrees of freedom that you need. Every time you increase your range of motion by adding a degree of freedom, you exponentially increase the computational problem of controlling that motion. So in practice, the range of possible solutions are usually obtained by imposing additional constraints. So far, we've mostly been describing what might be called numerically controlled machine tool, or a blind robot in an open control loop. But if we want a robot that knows whether its arm is in the right place, then here's where the sensors come into play. Sensors can measure the actual position of each joint and provide feedback to the controller for possible adjustments. The sensors are providing information to the controller. Is a joint at 45 degrees? Is a joint at 30 degrees? So Clawbot has external sensors, show you right here, to keep track of the motion of this part of the joint, and down below, Clawbot has external sensors to help with motion control. These are electrical switches that are used as limit sensors. When Clawbot moves its arm, if it moves to the end of its range, it hits a limit sensor which turns off the motor powering it. The sensors that robotic manipulators use to measure the position of their joints and end effectors vary. If the joints are powered by servo motors, sensory control is actually built into the motor. So I've got a servo motor here. Inside the servo, you have the electrical motor and the equivalent of what we call, underneath here, a potentiometer. I just pointed that out on Clawbot's arm. It's basically a volume knob. It's a variable resistor that signals angular position by changing voltage in a circuit. And then on the top of the servo here, we have a bunch of gears that connect up the motion of the motor and the potentiometer, which is right here. Now, instead of servos, many industrial robots use stepper motors, which are more powerful and precise than servo motors. But stepper motors don't have built-in sensors, so you have to use external sensors. Servo and stepper motors measure and adjust position continuously. Now, from the perspective of range of motion, one of the amazing things about adding a degree of freedom is that by the laws of combinatorics, the number of possible positions or states of our system explodes. The blue band represents any of an unimaginable large number of positions the tip of our robotic arm could occupy. I've copied a few of the circles created by our second linkage, the one that rotates thanks to joint B, to show you the geometry of how this works. In real industrial robots, the degrees of freedom that you add don't need to be kept in a plane. If you want your arm to reach around in 3 dimensions, then you need to have one axis, one joint that is oriented perpendicular to the axes of the other joints. The increased range of motion plus control over that motion is more flexible, and it gives what we call in robotics dexterity. We also call it that in humans too, right? So the challenge, as we increase the range of motion and dexterity, the complexity of our control system has to increase too. Let's look at some of the key approaches for handling the trade-offs between the range of motion and the control of motion. In 1973, the KUKA Robot Company made headlines when they introduced the first industrial robot with 6 degrees of freedom. The robot was called Famulus, and it was built for automotive manufacturing, as about 1/3 of the industrial robots are still today. Famulus was an articulated robot, which means it had any number of revolute joints. You'll see articulated robots in the food industry, for example. In a bread factory, KUKA robots pick up containers of bread and transfer them to pallets, building stacks of bread that will be carted off to market. A very different kind of manipulator is a Cartesian robot, which has 3 prismatic joints. Remember, those are telescopic joints, and the 3 prismatic joints are arranged perpendicular to each other. Because those joints are sliding, they can also be made into very long tracks into what are called gantry robots. The robots at the Mansueto Library at the University of Chicago are giant gantry robots. A spherical or polar robot replaces the revolute elbow joint of an articulated robot with a prismatic joint. The term sphere refers to the shape of the working space of the end effector. The Unimate robots were spherical robots, with a telescopic joint that allowed them to reach for a sample or to weld a particular spot and then retract to get out of the way. Because spherical robots have just 3 degrees of freedom, they too are easier to control than articulated robots, which now usually have 6. But because they lack a large range of motion, we tend not to see many spherical robots in operations these days. So in between the spherical robot and the Cartesian robots is the cylindrical robot, where the working space is a cylinder. To get this shape, we need the first joint to be prismatic, raising the arm up and down. A revolute joint spins to create a circle, and a second prismatic joint telescopes a revolute wrist joint. Cylindrical robots are used in applications like spot welding. Now, a big breakthrough for simplicity came in the late 1970s, when the first SCARA robots were developed, supposedly inspired by a Japanese-style folding screen. SCARA stands for Selective Compliance Assembly Robot Arm, but the trick was not in saying that, but in redesigning the work into a series of simpler tasks to suit the simpler robot. SCARA robots have 3 revolute joints, but unlike ordinary articulated robots, all 3 joints operate in the same plane, so that SCARA robots can move the end effector very precisely, more precisely than articulated robots. The end effector is located on a 4th joint, a prismatic joint that's perpendicular to the plane of the revolute joints. Because the 3 revolute joints aren't restricted in size by needing to move perpendicular to each other, SCARA robots can also have very large motors to power the joints, making them some of the fastest robotic manipulators available. SCARA robots are very good for things like the surprisingly difficult task of placing and tightening screws. I know I find that frustrating. While the early industrial robots did the same job all day long, day after day, a breakthrough for flexibility came with Puma robots. These were programmable robots. Puma stood for Programmable Universal Machine for Assembly, developed at Stanford and supported by General Motors. Finally, the world's fastest robotic manipulators are typically parallel robots. The idea is to build multiple arms in parallel, working together like pairs of arms. The trick here is to move rapidly without crushing the food. So the arms tend to be very low mass, and that allows very rapid accelerations and decelerations. Because robotic manipulators work very rapidly, often with a lot of power, part of the design of the robot is also to design the workplace. Safety is a big consideration. In 1979, in a Ford Motor casting plant, Robert Williams became the first human killed by a factory robot. Reports say that the robot had begun moving more slowly, and Williams tried to climb into a storage rack to remove parts by hand when he was hit in the head by the 1-ton robot, and he was killed instantly. The standard way to make it safe for humans and robots to work together is, well, to keep them from working together, at least physically. The work areas for industrial robots in traditional factories are very clearly defined, and humans are kept out of those areas, which are called safety cages. As you can imagine, though, these restrictions limit the work that robots do. What about creating a robot that can not only work solo, but also on an assembly line, and can do so next to a human without injury? Flexible, easy-to-use robots that can work alongside humans were the goal of Rodney Brooks when he created the company that is now called Rethink Robotics. Rethink created the robot Baxter, which it commercially released in 2012. Now let's compare Baxter to earlier industrial robots we've been discussing. First, Baxter is lightweight compared to standard industrial robots, weighing just 165 pounds without its pedestal, which is down below. For comparison, the popular KR210 R2700 extra robotic manipulator by KUKA weighs over 2,000 pounds. Now, Baxter has far less mass and hence can do far less damage. As a trade-off, and to be fair to KUKA, Baxter can also only lift a much smaller payload, about 5 pounds maximum. Now, second, most industrial robotic manipulators have 6 degrees of freedom in an arm. Baxter has 7. 1, 2, 3, 4, 5, 6, and 7 here. An extra degree of freedom is in that end effector manipulator. So the extra degrees of freedom gives Baxter the ability to make fine-scale movements and adjustments as it approaches a target and it places a target somewhere else. This gives Baxter more dexterity. Third point, Baxter has 2 industrial arms, and they each have dynamic awareness of each other. It's like we've got 2 robots welded together here, 2 machines in a single one. Okay, let me show you how they interact, which is not at all. There's a force field. When I try to bring these arms together, I'm actually trying to slam these arms together, and you can see they're bouncing apart. And that's just a really cool interference that's built into Baxter to keep it from the arms from slamming into each other. So Baxter's controller sends signals that keeps the arms apart. And here's the key, the arms have to know where they are, and the overall robot has to know where each of the arms are relative to each other. Fourth, even more important, Baxter's joints are compliant. See this sort of springiness that's in here? That's compliance. So because they're not stiff, when we interact with Baxter, its joints give way. And this compliance is made possible by serial elastic elements that are actually inside. We can't see them. That link the motors to the joints that they control. These elements are springs. And they make sure that if Baxter does happen to run into anything, like me, it will immediately pull on the spring and not send a lot of force from the motor into that collision. Fifth point, if you are running your own small manufacturing business, one of the great features of Baxter is you don't have to be an engineer to program it. You just grab onto the wrist here, like this, and then you guide Baxter to do the motions that you want it to do. That's so cool, right? Baxter learns by doing. Now, let's get Baxter to do what Taylor did in 1938. And his robot used bricks to build a structure. All right, so I'm going to set this up. We've previously trained Baxter to do this. Let's get him going here. All right, Baxter, do your thing. So what we're doing here is the kind of task that in 1938 Taylor had his robot do, which is to use bricks to construct a structure. Let's see if you can tell what we're making here as Baxter makes it. So this is dual pick and place tasks happening with each of these arms, which is really 2 different robots. We already know that they can't collide, so they're built to not interact, and you can see they're taking turns. So we've sequenced how they're working here. Okay, that final right arm is going to do the final move here of the pyramid. Oh, I gave it away. Asked you what it was. It's a pyramid structure that we've built here. Ta-da. Baxter has done the task here. Very cool. And remember, we programmed this in a matter of minutes. So Baxter's the next generation of robots for the factory. It's built to be easily and quickly programmed by direct training, and it's completely safe to operate around humans. So I can imagine having Baxter in a small factory setting where you produce different kinds of products on different days. It would be easy to adjust Baxter to the new object to move every day. Because Baxter's safe to be around, I wouldn't hesitate, for example, to have it loading up boxes with custom chocolates or electronics or whatever I was making in my sort of home office or home factory. Thanks, Baxter. But what's the trade-off? I know I keep asking that question, but there are always trade-offs in robotics. And Baxter, unfortunately, is no exception. Now, Baxter is lightweight, but the maximum weight he can actually handle is 5 pounds per arm. Baxter's easy to train, safe to work around, and highly dexterous with 7 degrees of freedom in both arms. However, Baxter is not as fast or precise as a SCARA or parallel robot, and not as powerful as the classic articulated robots that work in automobile factories. But that's all right. As one of the first collaborative robots, or cobots for short, Baxter is defining new roles for industrial robots and really helping to bridge from industrial robotics to what we are starting to call service robotics, where robots are designed from the start to interact safely with humans. Now, other robotic companies are also working to make robots more collaborative with humans. KUKA Robotics, one of the world's leaders in articulated industrial robots, is making slower, lightweight robots with compliant joints for work as service robots. So you can see where we've come with industrial robots. Starting with Taylor and Duvall, we have the origins of the robotic arm, a highly successful class of robots that has forever changed the nature of work in the factory. And now we have newer robots like Baxter, able to work alongside humans and able to learn by doing, so they can quickly be incorporated into lower volume, lighter load situations where the work changes quickly. It's the beginning of interactive robotics. So what do you say, Baxter? How about a high five? Yeah.